We're back later the same morning, and we're going to continue with erosion. We did erosion by gravity, mass wasting, slump and creep, mud flow, mudslide, landslide, and now we're going to do erosion by water. Loose sediments can be eroded by water that falls from the atmosphere. Raindrops strike the surface of the earth and lift particles of soil, sediment, and with enough rain, or if the ground is at or near saturation, can't hold any more water, and there is a negative slope going down or gradient, water will carry sediment. This is known as sheet erosion. So here you can see an old farm somewhere out west, a lot of rain, didn't put any crop on top of the soil to cover it over the winter, and the rain is carrying away his precious, or their precious, topsoil. Topsoil is the soil which has the most organic matter in it and therefore is very rich in terms of nutrients for the plants in next season's crop. Well, if you lose your topsoil, you're losing soil nutrients. Here's another one of sheet and rill erosion, right? So you get the sheet erosion, and then you get these little rills, which are ridges, and then these beautiful patterns, dendritic. They look like a leaf of little mini streams. And if there was a source of water that kept being released, let's say there was a spring, this might become a permanent stream. But this is just the effect of not covering the soil over the winter and allowing the erosion to occur. Here's another example of it, rill and sheet erosion. And again, you can see how what are almost permanent streams evolving, but eventually the farmer will cover this with some kind of crop and hopefully hold more soil than lose. Erosion by water in the stream. So this is off the field now, and we've created a permanent source of water somehow, and the stream begins to erode the land. And here we can see this stream is eroding away. This is called a cut bank. You can see the bank is being cut away, and if they keep allowing this cutting to go on, eventually this tree will be lost, and this homeowner or farmer is losing property to the stream. Well, that doesn't seem quite right. So they've tried to slow it down here by putting some boulders on the side to hold off the erosion, but they have a bigger problem here. And you can see actually they've already lost a tree. So erosion by water in a stream or river is quite important. So these words you need to know, and I would advise you to pause the video and make sure that you get these down. I'll probably give you some questions that will force you to do this if you want to do the job properly. But water flows downhill because of gravity, and streams begin at the head or source of the stream and end at the mouth. So the head or source at a high elevation, and the mouth where, say, the Hudson River enters the Atlantic Ocean. This is usually, again, the end of a stream. This is the mouth of a stream is usually into a larger body of water. So a stream enters into a pond or a lake, into a reservoir, right? Next, stream flow is contained within a channel or the stream bed and banks. So the bed is the bottom of the stream and the banks are the sides, and the channel is that central area where the water is moving at its greatest velocity. Source of water in the stream is from runoff over the land or seepage into the stream from groundwater. Those are the basic ways in which water gets into a stream. Seepage from groundwater or runoff as an effect of precipitation. Is that the right way to put that? Stream rate of flow is its discharge. So how fast is it going past a certain point? So the discharge of this stream looks pretty high. So at any given moment, there is a volume of water, right? A cubic volume of water passing a particular point. So you can often see this in the literature about streams, that the stream is moving with a certain discharge, cubic volume per second. You also see this on pipes in your bathroom or in kitchen. It'll say that the discharge of the pipe is 2 gallons per cubic foot. So every cubic foot of water of discharge would be a certain number of gallons. 2 streams merge. The smaller stream is called the tributary. So many streams have tributaries. Tributaries are ranked by number, right, going up to the smallest, down to the largest, into finally the main stream. The change in elevation of a stream from source to its mouth is called the stream's gradient, just like elevation gradient, pressure gradient, temperature gradient, the change over a distance. So from the source or head to its mouth, the gradient. Streams carry sediment via solution, suspension, saltation, and bedload. You need to know those words. Solution, the smallest sizes, these are dissolved minerals. These include salts. So things that have dissolved into the stream. Suspension, these can be clay particles, organic matter, silt, sand, depending on how fast the stream is going, right? So if it's a very fast stream, you'll have larger particles that are carried in suspension. Saltation, these would be the very largest particles that are bouncing along the bottom. So sand, pebbles, cobbles, boulders, they're bouncing along the stream bed. They're not normally lifted completely up into the bed unless the stream is moving at a very high rate. And then we have what is called bed load, right? The largest sizes are rolling along during heavy stream flow events. So from smallest to biggest, solution, suspension, saltation, and bed load. I shouldn't have implied that that all sizes can be suspended. That was a false, that is not actually true. I shouldn't have implied that. And I shouldn't imply that in saltation, the largest particle boulders are involved. The point of this list is that the sizes go up as we change category. Solution, the smallest sizes, suspension, the next largest, then saltation, then bed load. Again, we refer to this table on page 6, or this graphic on page 6 of the reference table, with how much velocity a stream needs to create a bed load of movement, to create a saltation of movement, to create suspension, and finally those objects that are in solution. And they can be in solution objects. Obviously, clay, silt, sand, pebbles are part of the bed load, right? Clay, silt, sand, pebbles are part of the saltation. Clay, silt, and sand are part of the suspension. And then smaller particles, or particles that have the capability of being dissolved, are in solution. This is just a funny little sign I saw up on Mount Hood, a volcano that goes up about, what's about 11,000 feet. I don't know how high, but a lot of people go hiking there. And of course, it's wilderness. There's not cell phone coverage, and there's no people wandering around waiting to rescue you. You're on your own. You have to be ready, and sometimes you have to go through, particularly this time of year, through a very fast-moving stream that's got snow melt in it, and so you need to be ready to get across that stream in a safe manner. And so here are some tips for getting across the stream, and hopefully you are not alone. So it says avoid hiking alone, check the weather. If there's sudden thunderstorms, that can raise the level of these mountain streams very quickly to the point where they're impassable, and you don't want to put your foot in it. So if you know there's going to be thunderstorms, you should be careful, because there's sometimes a thunderstorm and you're not even aware of it, but the stream has risen. Go across in the morning, and again, fast water, cold temperature, downstream hazard like a waterfall. You can't tell how deep it is. It's definitely higher than your net. And if you hear boulders rolling along the bottom, you don't necessarily want to cross it. Scout up and down the bank. Keep your pack on, but undo the hip and chest straps. Now, why would you do that? Why would you do that? Because you get rid of the pack if you have to. And make sure you have foot protection on, particularly for your ankles, so if it slips in a rock, you don't get abraded and a cut and you're on your own and it's bleeding and that's terrible. And have some support, a hiking stick or two. And you can see this beautiful way that you could do it walking side by side. This increases your mass and increases your stability. So, what's the approximate minimum stream velocity needed to keep a 6.4 centimeter diameter particle in motion? Well, let's go back and look. We need a 6.4 centimeter particle. So here we are. Well, that's the border of cobble and pebble. We just drop down, and it looks like 200 centimeters per second, or is it 150? Maybe more like 150. Let's go back and look. And no, about 200, okay? Definitely more than 100. So that's how you do that. You just go to the chart, you look for the size, 6.4, and then you drop down from the black line to the x-axis. Life cycle of streams. So streams are typically thought to have 3 stages. A young, youthful stage where there's no major channel, there's no flood plain where you get at a mature stage, and there's no area where the stream is easily meandering over a very flat, low gradient. High gradient in its young stage, up higher elevation, less gradient here, slower velocity, and the slowest velocity as it approaches its mouth, from source or head to mouth. So here would be young streams cut the land into what shape? So here's a young stream up high in the mountains. And what's the shape of our channel here? I think it's pretty obvious to see that we get, with stream erosion, the stream cuts downward over time. The banks erode, leaving a characteristic V-shaped valley. So you need to know that streams erode the area they go through, particularly the young, high elevation stream, into a V-shaped valley. We often see this in the mountains. So here again, a beautiful V-shaped valley, high up somewhere in the mountains. Or here, beautiful, I'm taking this picture from an airplane at 35,000 feet. We can see this beautiful V-shaped valley. I'm not sure what river this is. It may be the Salmon River out in Idaho/Eastern Oregon. Or here, this is more of a meander, but you can see here these beautiful little V-shaped valleys. And you can see this is called parallel stream form. So these parallel little mini streams that go down into this V shape. And then you see this larger river that has cut its way through the hills, finding the path of least resistance. But I really wanted you to see this V shape here. But all of these have an overall V shape, all of these areas. So how does water almost always move? Downhill. Water will always seek the lowest elevation it can reach, so it flows in valleys. But I did put a little asterisk here because capillarity in groundwater is an exception. Capillarity, remember, is where along the capillary fringe at the water table, water can crawl up against gravity. So it's not always quite downhill, but generally. Mature streams, the second stage, and rivers develop floodplains and terraces. So here what we have is that the land many years before had been at level T1. There was a stream up here, and it eroded away the land to T2. And the stream eroded away the land to T3. And now the stream is in T4 with these terraces that used to be where the stream existed, but the stream eroded away. Now, we have here a little floodplain where the stream gets too full and overflows its banks, part of the erosion of the current T3 terrace. Eventually, the stream will cut down and create a T4 terrace with T5 as the base. In old age, straight streams turn into meandering streams. So we had the V-shaped valleys in the young stream, the terracing in the middle age, and the straight streams that meander over very shallow sloped landscape heading towards their mouth. They often, these meanders, will get cut off and they'll form what's called an Oxbow Lake. So imagine that one time the stream is running so fast it just doesn't feel like going all the way around here. It's got too much water in it. It just cuts right through here. Well, this area can be cut off from the rest of the stream and it can become what's called an Oxbow Lake. So the stream doesn't want to go around the meander anymore, doesn't want to go around the curve anymore, cuts the corner and develops a new stream bed and leaves behind this beautiful Oxbow Lake. Here's your Oxbow Lake. Stream used to come, right? Somehow, I don't even know how it used to be. Maybe it was like this, but it lost that, right? And now it has this Oxbow Lake, and here it used to come somehow here. Now it's over here. So these streams are moving around. Here, I took this picture from the air. Here's the actual stream, right? And you can see where it formed these Oxbow Lakes, where they cut off part of the channel. This is kind of a famous oxbow, but it's not a lake. So I'm up in the hills of southern France with my wife at a place called Cirque de Navicelle, and this area here is a little raised hill, and there's a little village here, some houses, and there's a river that flows back here. Well, the river used to flow around the hill, but over time, that would have been 6,000 years ago. So 6,000 years ago, the river flowed around the hill. This would have been what it looked like 6,000 years ago. This is the explanation in French, all right? And then, maybe Miss Seme can come and translate. Then, in that period, it stopped going around here. I guess the flow was too great, and it cut this area off, and we ended up with this beautiful little village down in the bottom of this gorge with the river flowing back. And by the way, there's waterfalls back here. This is a beautiful place to go. Gorgeous. You have to climb down a beautiful hike, or you can drive down. It's a steep slope. It's a very narrow road. One of the world's most dangerous roads, according to the internet. And there's a little cafe here. I got a delicious Coca-Cola. Oh, it tasted so good. And here's a beautiful, this is from a trip I took across the country in 2019 in the spring to go to Oregon. And you can see these amazing meanders on a river that's come out of the mountains. And you can see where the stream has a floodplain. These flatter, lighter color areas are areas where the stream can leave its banks and flood the ground, which actually ends up making beautiful farmland. So you often see that. Some of the features of a stream that's eroding, the main feature of a stream that's eroding would be its Oxbow Lake and its cut bank. So here's the stream flowing down. And interestingly enough, if we started a race, right, at this point, and threw two oranges, one on this side and one on this side, and watched the oranges go, by the time they got down here, they would be passing together. The water would all flow together. It doesn't slip and slide, some water going ahead of the other. That's because on the inside of the turn, it's going slower and we're depositing sediment. On the outside of the turn, it's going faster and we're cutting the bank. Therefore, we have a cut bank and a cut bank and a cut bank and a cut bank. Meanwhile, slower water, depositing, 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 depositing. But since we're concerned with erosion right now, we're going to focus on the cut bank. That's what we need to think about. That's the erosive part of the stream. The water moving faster on the outside. Now it's moving faster, and it ends up going a longer distance. Ends up going, must go a shorter distance, and the slower water, it goes a longer distance, and the slower water goes a shorter distance, right? And it ends up together. Overall, it averages out. As streams meander, water moves at different velocities on either side of the stream. The outer side of each meander moves faster than the inner side. The outer side is erosive, is eroded, and is called the cut bank. General rule, stream velocity is at its greatest in the straight reach of a river in the middle. So where the stream is straight, right, nowhere there, but like here, if this is a stream, the straight part is where the water goes the fastest, and it's in the middle. So if you fall out of your boat while fishing, this is where the stream is faster. So swim perpendicular to the flow and you'll get over to the riverbank. All right? The water is moving slowest on the sides. The higher the velocity of any stream or river, the further it will carry its bed load of sediment, the stuff that it is carrying from boulder to clay. In general, streams and rivers that reach the sea are carrying smaller rather than larger sediments, silt and clays, by the time they reach the mouth. So one of the reasons that the Hudson River will always look brown, particularly in the spring, is it's carrying a lot of sediment. It's not got garbage in it. It's sediment. It's clay and silt that came from the land up as far as the Adirondacks, where little particles of sediment entered a stream and then entered the river and then were carried down to the mouth. These are different stream patterns that can develop. I mentioned a parallel one earlier. So you see a stream that goes down with tributaries going into it. So this would be off of a round mountain, right, made of different rocks. This was also off of like a volcano. This would be in a delta. This is often on a plain. Rectangulars in the mountains, parallel mountains. We don't have to look at them in too much detail. Here's your terraces. I should have put this before. This is your mature stage stream, and these are those terraces. These are where the stream used to exist. So it's down at this level. Used to be way up here. It's eroded away all this land and created terraces where occasionally the stream will flood. So this is a stream terrace. Here's a floodplain of that mature stream, not quite straight, so it's not as high velocity. So now we're in the mid stage, and this would be the area that would flood when the water is high. So with that, we will stop with our second section.